Um, while Good Noodle is fixing his mic issues, did you have any questions for me, Shauna?
Yeah, I did. Just give me 1 second.
Yeah, sure.
I'm actually for the problem. The solution is just.
Hello?
There we go. I can hear you.
Hello.
All right. Let me get my markers out. Besides the question you asked me about your project, did you have any other ones, Good Noodle?
I don't think so.
Okay.
Yes. Is no one else here?
No, Shauna's here, so we'll go over hers first, and then.
Oh, okay.
And then if we have time, we can talk about your project.
Sounds good.
You're good. No worries.
No, I think I'm actually fine.
Okay. Let's see then. Well, if you have any questions, just let me know. But I guess in the meantime, I'll very quickly discuss with you, Good Noodle, the problem you asking me about your project, which was difficulty with generating the boxes on the screen.
Yes.
Yeah. So you guys already have, you guys were already given the module for creating filled-in, like one filled-in box, yeah? For the
yes.
VGA and lab. And so you were able to move it around and like change the size, yeah?
Yes.
And the way you did that is you just changed the numbers that you send in as the inputs for the X and the Y bounds. Because if you change the X and the Y bounds, that changes the top left and bottom right corners of the box. So basically it draws it in a different position. So if you want to do one box, you instantiate that module once. And if you want to do many boxes, you instantiate multiple of that same module, just with different X and Y values for each instance. That's how you would get many boxes.
And then to give it like a specific pattern, I would probably just use like some type of logic for that, right?
When you say a pattern, what do you mean by a pattern? Like the coloring of the box?
That's one of them, yes. 'Cause essentially we wanted to make it so that it spawns at the very beginning, at the very least. It spawns one like iteratively, one at a time, and it makes like a cycling pattern down to the middle.
And so well, yeah, I mean, it depends on the kind of pattern that you're talking about. So you're saying you make a box, and then your boxes appear in front of you on the screen in a specific order? Is that the pattern you're referring to? Or
with the diagram I sent you,
Yep.
it's kind of like more like that in that or maybe we're saying the same thing. It's just that like they're like spaced out evenly, and then but at the very end, it's like in the middle, just so that just so that it's all filled in. I'll work that out myself. However, I'm just so you're saying that to spawn multiple of these rectangles, I just need to instantiate these boxes, and then how do you think I would be able to then sorry, I'm blanking here.
No, you're good. No worries. sometimes it can be difficult to know what questions you have.
Yeah. What I was thinking is that essentially our game is just we have these multiple rectangles,
Right.
and then at the very first rectangle it's going to light up, and then we have a destination rectangle that we want our lights to match essentially.
Okay.
Yes, and then if they match, and then the user presses like a push button or whatever, then and if it hits that rectangle, then they get a point. And if not,
So
then
wait, you're saying it hits the rectangle. What's hitting the rectangle though?
essentially we have like the game rectangle and then the user's rectangle, and the user's rectangle will start at the first rectangle, and then it's going to keep
So it's like
going.
overlaid on top of one of those other 9 rectangles you have.
Yes.
Okay, and so like they can move it, and it'll jump between the different rectangles, essentially.
Yes.
Okay. Okay. Yes. So. I mean, the main thing that would happen is you would essentially have that rectangle module, and the output of each of those rectangles is out of each of those rectangle generator modules is just a 1 or a 0. It's 1 if you are within the rectangle bounds, and it's a 0 if you're outside. And so that signal for each of those rectangle generator modules that you instantiate, you can feed those into combinational logic to determine what colors you want each of the pixels to be. So, for example, if the output of the first rectangle generator is a 1, then color that pixel green. And if the output is within box 2, so if the output of rect gen 2 is 1, then color it black. You don't want to color it. And then basically you would have combinational logic to decide, depending on the state of each rectangle, what to color it. So if that rectangle is in the selected by the user state, you'd make it yellow. And if it's in the destination state, make it red. And if it's in the starting state, you make it green or something. And if it's none of them, make it blank, all black. That's the first thing that comes to my mind when you're talking about like how to color them.
Okay, thank you.
Yeah. Okay. Did you have any questions, Shauna?
No, I mean, I have a couple of things, like, if there's no other questions that, just as a refresher, I don't know. So I was thinking, I don't even know if this will be on the exam, but like, just like a very simple, I've done this a million times, like a parameterized system Verilog module
Mm-hmm.
was one thing I was like, and then another one is like a simple making an array in RISC-V. There was one homework question where I was like, I don't remember this.
Okay.
I don't know. I mean, it's stuff that I could just like keep going through the homework for.
Well, for the parameterized modules, I know she has like one example in the set of files.
I know it's easy. I think I just need to write it on my cheat sheet.
That's fine.
Okay, yeah, we can probably skip that one. I don't even know if that would be on there, but let's see, there was something with, oh, here we go. So, I don't know. It's not like I have questions about this. I think I just need
Okay. Well, if you have any examples you want me to go over, that's fine too. What about you, Good Noodle? Any questions?
Uh, um, Going on the parameterized modules, I saw on the VGA or in the VGA SV that we have that there is the parameterized module. However, like it was more to set up like dimensions for our screen. Like what? Why would you use that instead of maybe like a logic inside of your VGA inside of your module?
So the main reason why you use parameters is if you want to easily be able to recompile your code and have the hardware basically get bigger or smaller in terms of, the numbers. So oftentimes like constants, so just a number that you're going to be using in your code, like the binary representation of 7 or something like that. You might parameterize that because you maybe want to change the 7 to be an 8 later in a different instance, and you just don't want to have to make 2 separate modules for that. So the main reason why you don't write it as internal logic is, well, I mean, there isn't necessarily a reason why you can't do it as internal logic. The nice thing about doing it as a parameter, though, is that when you instantiate it, you can then change whatever it is. Because if you do it internally, that's fixed. You can't then change change it when you do an instantiation. The parameters are fixed.
I see. Thank you.
Mm-hmm.
Good Noodle, did you have any questions, like for the exam? Or can I ask kind of unrelated question?
Not really. I just need to go over on the parameterized. Like, I feel as though the hardware portion, like System Verilog, might like give me a harder time than the RISC-V and the machine code. Because I mean, if it was the machine code and we're given the Appendix B, then we just gotta fill in the blank there. But I haven't studied the System Verilog in a while.
That is my like fear as well. Like I feel
Mhm.
like RISC-V is really straightforward because you can have like your C and then you do your RISC. But
Mhm.
like
Yeah.
System Verilog is just like what the hell is going on? To me at least, that's like what I'm probably most scared of for this test.
Mhm.
System Verilog. Yeah, and it's like how many things do you put on your cheat sheet for System Verilog? Because I did ask her during the review, and she said she would give us like a like the snippet of the code to modify. Like, I don't think she said we'd have to like write anything from scratch, and definitely no test bench. So, yeah. Because I know we had a parameterized module in one of the homeworks, like I think it was 9, that would be covered by the midterm. So,
I mean, it's possible she might ask a question like, here's a module, parameterize it. That's a possibility.
yeah, I was definitely going to add the parameter to, I think it was, what was it, reg? It was reg,
I didn't even think about doing parameterized until right now. So thank you very much.
yeah, I'm just pulling up the homework assignment it was on. I think it was 9.
I believe this is on 8.
Was it 8? Yeah, it was either 8 or 9. Let's see.
Yeah, homework 8 assignment or question 3.
Yes. Yeah, maybe, do we want to just go through that?
Yeah.
I mean, I'm looking at the answer and it's only like a few lines. It's really just like parameter n equals whatever. And then like for your data and your output, do the same thing. But yeah, can we just go through it maybe?
Yeah, sure. Let me pull up. You said it was homework 8, question 3?
Yes.
Okay.
And it's based off the flop RC. Like, can we maybe write it unparameterized and then parameterize it?
Yeah, we can do that. Assignments. And homework 8.
Victor,
Yep.
when you said something about the parameterize and you can change it, you're talking about that when you instantiate it, right? Like you can
Correct.
change. Oh, okay, that makes sense. That makes more sense now.
Yep.
Yeah.
Okay, so parameterize or create a parameterized module, regNR, design a parameterized n-bit, synchronously resettable register, inputs are clock, reset D, output is Q, D and Q are both n-bit symbols. Okay, so yeah, we'll start by making it just a like a 4-bit register, and then we can parameterize it. So the first thing we do whenever we're making a module is we use the keyword module. And then that's followed by the name of our module, which in this case is regNR. And I'm going to go ahead and not fill this in, but this is where I'm going to start putting my parameters. I'm not going to fill it in right now, and you wouldn't put that if it was an unparameterized module. I just want to make sure I have space. And then after that is when you put in the port list for your module. So in this case, we have a few inputs. We're told that clock, reset, and D are all inputs. So I can say, firstly, so the first thing I can write down is the input logic signals for clock and reset. And those are always 1-bit values, even if I was to parameterize this, so I don't have to worry about making it parameterized or anything like that. And then the next set of signals is going to be my D input. And I missed a comma. And the last thing that I'm going to add in is the output, which is called Q. So that's my port list. And again, I have a 4-bit flip-flop here, so what this is going to eventually instantiate is something that looks like this. So with that out of the way, now I need to make my flip-flop. And so the way I do that is I have an always statement. So I say always underscore FF for a flip-flop. And then I dictate what the sensitivity list is going to be by doing my @ symbol. And then inside I put what the flip-flop should respond to. So we always put the clock. Depending on what kind of clock, you'd either put pause edge or neg edge, or you could put both. And then depending on what kind of flip-flop it is, specifically if it has an asynchronous signal, we'd put that in the sensitivity list too. However, in this example, there are only synchronous signals. There are no asynchronous ones, so we don't put anything else in the flip list.
Wait, I asked you this before, it's somewhere in the notes. If it was asynchronous, it wouldn't be a pause edge, right? Our sensitivity list would be based on.
Well, it depends on what the signal is. So, like, if it's a reset signal, so if it's like a high asserted reset signal, which is to say that if you input 1 for the reset, that means reset it, then yeah, you would put pause edge reset.
Yeah, okay.
Yeah. Or pause edge set.
Yeah.
Yeah. But here, no asynchronous. Instead, however, on the inside, even though this is synchronous, we don't put the reset in the sensitivity list. We do still have to account for that inside the body of the always block, where we say, okay, well, if reset is true, we want the output Q, or in other words, the value stored in the register, to be 0. And otherwise, we want this to behave like a normal flip-flop. We want Q to receive the value of D. And that's the entirety of the code.
Could we do something like assign Q equals?
So assign is exclusively for combinational logic.
Oh,
You
okay.
don't use assign for sequential stuff.
That's awful. Okay, so for sequential, let me do this.
Yes, whenever you're doing sequential things, you're going to be using some sort of always block like this.
Okay. Okay, thank you.
Yep. And for you guys specifically, it's almost always going to be always FF for this class. You can use like an always com block for combinational logic. That's an always block, but you use it for combinational. But this one's specifically for sequential stuff. Okay, so any questions on this start? Okay, so the next thing we want to do is we want to, like I mentioned, parameterize the bit width of this register. So, get the eraser. What we want to end up changing is we want to add in a parameter into our parameter list here, which I'm going to do. So I'll call that parameter width to represent the bit width of my system. And before I write the word width, I actually have to write parameter. So I write that in. If I was to want a default such that when I instantiate this later, if I don't put anything in the instantiation, I can just assume a default. I can put that here like so. So if when I instantiate this module, I just say reg nr, and I don't put the, something like this, if I don't use a parameter list when I do the instantiation, it's going to assume by default 4. Whereas if I were not to put this, there is no default in what I would have to write #5 or #4 for whatever it is. So that's optional, you don't need to put that. And then if I was to put any other parameters, it would be with a comma, followed by the exact same syntax, parameter, name of the parameter, and then default if there is one. However, in this case, there are none more that we care about, so I'm just going to end the parentheses there. Okay, so that's the easy part. Now, what do I change in the code to account for this parameter?
Our bit width for inputs and outputs.
Yeah, we changed the bit widths for D and Q. Specifically, what do we replace them with?
So minus 1.
So if we want a bit width of 4, that means that we should say 3:0. So it's always going to be 1 less than the width, :0.
Oh, you mean the commas.
Yes. If you were just to say width -1, that would be a single bit. Yeah, it would just be a single bit signal. And that's the only change we actually have to make for this particular module. Now, depending on your module contents, you might have parameters that go inside the actual body of the code. They don't have to just be here in the port list. This is more of just like an introduction to what a parameterized module is, and simple things that you can do to make your life easier, so that I don't have to make a module for a 1-bit and a 2-bit and a 3-bit register.
So, like, let's say. Sorry, good
Yep.
noodle. Did you have any questions before I like launch into it?
No, I'm fine.
I did miss that module.
Yeah.
Now we're
So I think one of my questions, like as I was going along with the project, so if we're doing like the structural coding with all these modules, so you answered my question about like instantiating it.
Yeah.
But like, can you, if Good Noodle doesn't mind, can we just go through like how you would make that wire and like then like get that information out of the module?
What do you mean, get the information out of it? Like how you would like
Like when we do wires.
wire it with other things?
Yeah, like when you have your structural module, your structural modules, and like you call your basically functions, your modules.
Yeah.
Like, I know we were like, I'm just so bad at the structural stuff. Like, I know we were like assigning it to wires before.
Yeah,
Like,
so why don't I go ahead and create the following. So I'll maybe do this. I'll call this, for shorthand, I'm just going to write R to represent this. So this is going to be an instantiation of R. This is going to be an instantiation of R. And then maybe I'll AND those and store it into another instantiation of R. So this is a structural style of coding for the most part, besides this AND gate, but occasionally you will see structural styles have like one or two AND or OR gates sitting in there, just because there's no reason to separate that into its own module. It's kind of unnecessary. So each of these are going to have a reset signal, they're each going to have a clock signal. So this is the module we want to create now. So what I'm going to do is I'm going to go ahead and erase this stuff, the actual content of my module, but I'll leave this port list and parameter list up here so that I can remember how to instantiate it. So this is a big black box, and what we're going to do is I'm going to call it maybe test. So I'll call it my test module. And I could actually parameterize this if I wanted to, but I think what I'll do is I won't, though you absolutely could parameterize it, just like we did for this one, with the pound sign and put the parameter, and then you can instantiate this as a parameterized module externally. Doesn't really matter. For the moment, though, I won't do that. Instead, I'm just going to consider my inputs and my outputs. So for this whole system, I have some data coming in here and here. I have a clock for all my signals and a reset for all my signals and a data coming out. So what I'm going to do is I'll go ahead and write all of those in my port list. So I have first clock and reset. And then I have some data inputs. So I'll call these 3 to 0. Call this data A, I'll call this data B. And then we have an output here, which is, I guess I'll call a result. And so now what I want to do is I want to create or instantiate each of these units, each of these modules within this bigger structural module. And so the way that I go about that is I call it using the name of the module that I care about. So I'd first start with, so I first specify what is the name of that module, and then I need to give it any parameters that it might have. So in this case, I'd say $4. I could omit this because I have a default parameter, but I'm going to put it in there. And then the next thing that you have is you're going to specify the instance name. So the instance is this particular register versus this particular register. They're the same physically, they're the same internals, but the things we're wiring them up to are different, and so we have to specify them with different names. So for example, I could call this one R1, R2, and R3. Or I could call it whatever I want. I think I'll do RA, RB, and R out. RA, RB, R out. I think that's what I'll do. So I'll call this one RA. And then I have to give it its port list. So the first thing that I feed into RA is the clock signal. All of these registers in this case share the same clock, so I'm just going to put clock here because that's the first thing that pops up in the port list. The next thing that this needs in the port list is its reset signal, and all of these are sharing the same reset, so I'll just put reset. Now the next thing it needs is its data. For RA, the data input is data A, so I would put that here.
You don't need to put like in because it's specified in your.
I wouldn't need to put what?
Or you don't need to put the like 3.10 port.
Oh, good question, yeah. So if I want to use the entirety of the signal, I can just specify the signal name itself. That means the entire thing. If I wanted parts of it, yes, then I would have to specify the widths.
You would put like data A and then in brackets.
Like 2 to 0.
Yeah.
Yeah. But here, since I'm using the whole thing, I can just use the name. And then for the last part, I have to specify the output. So the output here is actually an internal wire. So normally you'd put internal logic kind of above your instantiations, but for the sake of space and also just because I can, I'll put them below. So I have to specify a few internal wires. This one, and that one. So I guess I'll call them, let's do this, logic 3 to 0, and I'll call this one A out, B out, and I'll call this one RN, just to give them names. And that's just the names of those wires. It doesn't really matter what you name them.
Victor?
Yes.
Sorry, really quick, like what Shauna said, so if at the very right of A out, we can specify the bit, right?
Yep.
With, oh, okay. I was just wondering about
for
that.
For example, right here, I want to put A out, so I can write that two ways. I can either just put A out, or I could write it like this. Those mean the same thing. So I could just leave it as A out, or I could put A out brackets 3:0.
Wait, so we can, it doesn't go from top to bottom when it reads the code? You can.
It all happens in pair. I'm pretty sure you can. I may be incorrect, but I just don't have space.
Yeah.
But just generally, you declare all of your internal signals above the actual content of your module. So you would typically see this up here. I don't remember if it's fine if it gets unhappy. Most other things you can do out of order. It doesn't really matter because there isn't really an order. But it might be unhappy if you don't declare these at the top. I don't recall. As for the rest of these, the exact same start of my declaration occurs with a different instance name depending on which instance I'm doing. So this one will be RB, and this one will be ROut. It happens that all of these instances use the same clock, though they don't necessarily need to. It's just for this design they are. And same thing for the reset. They don't need to necessarily use the same reset. I just happen to be using the same reset signal. However, they do all have different data inputs. For RB, the data input is data B. And for ROut, the data input is RN. And then for the outputs, they also have different ones. For RB, the output is called Bout. And for ROut, the data output is called result. And so now we're almost done. We've instantiated all the modules, all the blocks, and we've interconnected most of them. The only thing we haven't done was this AND gate. So all I would have to do there is I would just say assign, and I'm assigning Rn equal to Aout and Bout. Remember that when I do the single ampersand, that's the bitwise operation, which is what I'm doing here. Because you'll notice this is a 4-bit input AND gate. So you read in a 4-bit number, AND it with another 4-bit number, and your output is also 4 bits. That's what this does. And I'm done. So this is kind of the structure for a structural module.
This is exactly answering my question.
Good.
I was having trouble seeing where everything was fitting into everything else. One quick question for combinational logic: when we do assign y equals s question mark d1 colon d2.
Yeah.
That's saying assign s into y if d1 equals 1, or else d0 equals 1. Is that what we're saying?
Let me write it down and then I can tell you. So you said assign y equal to s question mark d0, or I'll call that d1. D0. So this is called the ternary operator. And what it does is it's the same as the following. If s, so if s is true, then y is going to be assigned the first thing in that list, which is d1. Else, which is to say s is false, y is going to be assigned the value of the second thing in that list, a d0. So that's what that corresponds to. And so this is like an easy way to instantiate a multiplexer, because this is by definition what a multiplexer does. If the select line is 0, you select the bit coming into input 0. And if the select line is bit 1, you select the input coming into bit 1 and output it to 1. So that HDL code would instantiate something like this. And of course, there's underlying logic as well.
Yeah, so then if we had 4 inputs, so our select line would be what, two different select line, or 2-bit select line?
Yeah.
So then we would have to do if s bracket.
So
1.
once it's past 2, you can do it that way, yeah. Once it's past 2, I would just do it as a combinational block. So I would do, I would probably just do a case statement, like an always block and then a case statement, if it's that many, because there's no need to do it with ternary operator. Can be quite a bit to get into.
It's a little tricky.
Okay. Any other questions?
question.
Yep.
Back to machine code. So when we have when we're going from machine code to instruction.
Yes.
No, I don't know.
No worries, you're good.
Okay, I do have a question. So when we're going from machine code to RISC-V,
Yes.
and we have, for example, a code. I think maybe I can just show this to you.
Yeah, go for it.
It's a little hard to read, but so when we have like a BLT or any sort of branch where we're jumping, so I was like writing the label is like how many instructions, but when I was just putting it into an instruction, like I don't include this anywhere. I don't know if that makes sense.
So when you do a branch, when you write it in assembly, you put the label name because the label is somewhere in your code. But it actually, so if you looked on Venus, it would actually show it decoded with, instead of this being L1, I think it shows it as the address that it's going to be jumping
I
to.
think so. Yeah.
So you would put that instead.
Okay. Yeah, I think I was more like for like the sake of a test. I don't think we use this anymore.
You would just put it there, yeah.
Okay.
Yeah.
I guess I could just put it there. Okay. I think I'll just write.
I'm sorry, was that for the branch like jump and link instructions where like we have our offset
Yeah.
Yeah.
and then like
I was like,
do you think it'd be fun?
Oh, sorry. Go ahead.
You can go first. You can go first.
Oh no, I was just questioning like when we're actually writing the instruction out. I was just like writing label, but it was like it was being offset by like, for example, 4 instructions. And I was looking through the solutions, homework solutions, and I didn't think Dr. Harris was like writing that anywhere.
Mm-hmm.
She was just writing like label. So I didn't know if we needed to actually include that.
That would have been great. So like saying this versus that.
Mm-hmm.
Right. Yeah. Yeah.
Or, well, I should probably put it as the actual value, which was, what was it, hex 10 you said?
Yeah, I think for that one was hex 10.
Yeah. So, either one of these should work fine. As long as you calculate the correct value. Even if you write it like this and you just write off to the side, hey, this label is positioned hex 10 units, or hex, what would it be, 4 addresses after this current one, that's fine.
That's called the jump target address, right?
Yeah, I believe so. I believe that's the formal name for it.
Okay.
Okay, and then we can only load 12-bit immediates into a register using add-i. If it's over 12 bits, we have to use add-i.
Yes.
And then we look at bit 11 equals 1. Noodle, do you have like a lot of stuff on your cheat sheet? Because mine is like really small writing, but I feel like I have a lot on there.
I'm sorry, what was that?
Is your cheat sheet like packed, or do you only have like a few things?
My cheat sheet for sure has the ALU and then the comparator stuff.
Yeah.
I don't, to be honest, I don't know what else to add.
I know, like for mine, I was like adding just some instructions, even though the instructions are all on the appendix 2.
Yeah.
But like, I feel like I'm gonna blank or something. So I'm just like writing it down just in case
I mean, if you
blank
have
out.
if you have a lot more space, just write big and like outline your sections by like names and stuff, so it's very
Yeah.
easy to find what you're looking for.
Yeah.
Mhm.
I like literally drew the entire ALU because I'm like really afraid I'm just gonna forget that, and like the comparator like tables, like what I need to compare. But yeah, I don't know what else. I feel like I'm missing something. Leaf instruction. Since we have like 14 minutes,
Yeah.
can we just go through like a very basic recursion?
Sure.
Like something super basic with just like maybe 2 calls or something. It doesn't have to be crazy.
Also, Shannon.
Was that?
Shannon?
Yeah.
You said you were taking Trio 2?
301.
Oh, 301?
Yeah.
You're not taking 300?
You should take it. I don't know, Victor, did you use Physics 180 and 301?
Physics?
Yeah, because it's like
That's a prerequisite for 301?
for the advanced standing to get into 301.
Oh, no.
Yeah.
No, you don't need to know Physics
Okay.
181 for that.
Yeah, good. I think you should petition to get into it.
I talked to an advisor, and they put me in 300 instead. Because I think 300 is a requisite for, is required for CPE, right?
It's not for 301 though. So Dr. Harris was telling me, she was like, oh, if you enjoy like building things, like you'll probably enjoy 301 and you should maybe take it next semester. And I remember she said something about that in class, like,
Yeah, because it's only available in spring, right?
yeah,
Mm-hmm.
yeah. So like, she definitely told me like look in 301 and not 300. I mean, eventually 300, obviously, but so. Yeah, it's gonna be a party in 301. We can keep up our like little study sessions. I don't know, Victor, you're probably not gonna like tutor it, but
Oh, at 301?
we'll
I'll
have
not
to
be
find
teeing for
something.
301.
Okay.
Okay, so I'll just do a. What would be a good one? Yeah, let's do that. I was gonna do factorial again, but that's kind of boring. So we'll do power instead, like exponentiation.
Okay.
And power. And so recall that for any base b to the power a, that's the same thing as saying b times itself a number of times. And I guess just to make it quicker, I'll just go through the actual code of deriving the C code. So we have a base case, and the base case is going to be if the power is 0. And I'm going to assume these are all unsigned integers just for the sake of my sanity. So if the power is 0, that's our base case, then we can just return 1. Because remember that any number to the 0, unless it's 0, is always going to be 1. So I'll be assuming for the case of this that the base is positive and that the power is non-negative. You would account for these cases separately if you had to include like the base equals 0, because you can't have the 0 to the 0 case and whatnot. So I'll just ignore those, make my life a little easier. So otherwise, then what we want to do is we want to return and we're going to call the power function. So I'll do this. This is a multiplication, by the way, not a pointer. So power of whatever the base is, and then to the power of, I probably shouldn't name these the same thing, huh?
Yeah, because should we multiply it to the power times power?
I'll just do POW for the actual function that you guys use in C. So pow base 2 power minus 1. And it's going to be that times your base. Because what we're saying here is that b to the a is the same thing as b times b to the a minus 1. That's what we're doing here effectively. We're taking my base and saying, well, that's the same thing, b to the a is the same thing as my base times my base to the same power but minus 1. And so you're slowly going to recurse down until you get down to the base case of 0. And then it's going to replace it with 1. It's going to return that. And it's going to be base times 1, so that's going to be base. And then it's going to return that. It's going to be base times base, so base squared, and so on.
So you could do power equals 1, return the base also.
Yes, but then I would have to put another other base case for if it equals 0. Because then if they call it with the parameter 0, it's never going to hit the base case, which is why I did 0 for the base case. Because if in int main they say
Oh, okay.
3, 0, then my function doesn't handle it. That's why I did 0.
Right. Okay, I get it.
Okay. So now what I want to do is I want to create the equivalent RISC-V assembly code, which corresponds to this. And so the first thing you do is you start with your function name at the top. So a label which corresponds to your function, which it can be called from. So I'll go and do that. So we have a function here called pow. And the first thing we want to check, and this is we're going to do this in 2 passes. The first pass is just don't think recursive stuff, and then afterwards we worry about stack operations. So the first thing I do is I'm trying to check my base case, which is if power equals 0. So I would have to check, what is power stored in?
That's A1.
Yeah. So here, base, that's A0. Power is equal to A1. And so what I do is I compare power to 0. So I can say branch, and I want to branch if these are not equal, i.e. I want to move on to the return statement if these are not equal. Branch if not equal, and the 2 things I'm comparing are power, which is A1, to the 0 register. And I'm going to branch to my, I guess I'll call it recurse. Because this label means I'm going to do my recursive stuff. But if I don't branch, that means I'm going to execute this next line, which is just your return. So in that case, all I have to do is say, well, I'm going to set A0 equal to 1, because that's what I return. Add I, A0, 0, 1. And then I can do a JR array. So I check if I'm in my base case. If I am, I'm not going to branch, and instead I'm going to assign my return value to 1, and then return for my function call. Now, if I do a recursive step, I'm going to need to do a few things. I mentioned that I'm not going to add the stack stuff yet, and I'm not, but I'm going to leave a space here for it, because this is where I'd have to end up doing stack stuff. What I would do now is I would say, okay, well, I'm going to multiply two things. I'm going to do a base times the result of the function call. Okay, so what that means is I have to call my function, and then after that, I can, once my function call's over, take the result of that, multiply it by the base, and then I will get my final answer that I want. So, before my function call, I'm going to save my base into a register. That's because when I do my function call, it's going to override A0, and base is an A0. So I kind of need that.
Mm-hmm.
So what I'm going to do is I'm going to say add, and I'm going to store this in T0. And the value I'm going to store is going to be A0 with the 0 register. So in other words, I'm moving A0 into T0. And then I'm going to go ahead and call my function so I can figure out what this recursive call returns. Right before I call it, though, I need to make sure that my parameters are initialized properly. So base needs to be the same value as base, which in this case is, well, A0, it already is base. That's fine. But power needs to be decremented. So I'll go ahead and do add immediate, and I'm going to take power, which was A1, and I'm going to decrement it by 1. So I take A1, subtract it by 1, and store it back into A1. Okay, so the last thing I'm going to do is I'm going to do my function call here. So my function call is going to be jump and link, and then I'm going to say the name of the label I'm jumping to, which is power. So I initialize my parameter, A1, A0 is already initialized. I do my jump to my function, and after this, well, that means that my function has actually finished returning. So all I have to do is multiply the return value by the base, and then I can return that. Here, I want my base was stored in T0, so I can say, okay, well, I'm going to take the multiplication of two numbers. I'm going to take T0 multiplied by A0. That's these two. So I'm going to multiply my base times the return of my function call, and I'm going to store A0 because that's where I return with. That's the register I return with. And now that I've finished that calculation, I can actually return to my caller. And again, there are a few things I have to add specifically for stack operations. And specifically, it's going to go here. So any questions on that first pass?
So T0 has our original base in there.
Yep.
And we stored it in there because we will be changing A0 as we return it.
Yep.
Okay. Could we have instead saved to the stack A0 right there, and then after we get done with all the stuff, but then we'd have to put the return in another temporary register and then restore A0 to the original
So the answer to your
base.
question is yes.
Yeah.
But we'd end up having to use another register anyways.
We'd have to, yes.
So I was
okay.
like, I'll just use it here.
I got
Why
it.
not?
Thank you.
So if we want to allocate stack space, first we say, okay, well, add immediate, and the thing I'm allocating stack space with is SP. And I'm going to say minus, right now I'm going to say -4, because I'm not sure what I want to save. I definitely always want to save RA though, so I'll go ahead and list that down. So to save RA, I need to say, well, I'm going to do a store word. I'm going to store RA at offset 0 of SP. And so that's going to save RA on my stack. So now if I was to do this, if I was to just save this here and then restore it afterwards with a load word and a restoring of the stack pointer, I would need to make sure that I don't need to save anything else. And as was hinted at before, you need to somehow preserve the base value, A0. And in this case, I did so by storing in T0. Now, for the sake of this code, T0 is always going to be the base. When you do a recursive function call, it overrides T0, but with the base again.
Mm-hmm.
So it doesn't really, well, T0 doesn't change. It's always the base. If it did change iteration, we would for sure have to save it in stack. And just since that could be a case where, if we did have some recursive function that did change every time, I'm going to do that for this one, even though it's not strictly necessary. I don't have to do it. So I'll go ahead and save that one stack as well. Okay. Any questions so far?
Wait. Oh, no, so far no.
No questions from me either.
Okay. So let's go ahead and trace this out. I'm going to fill in the stuff down here, and we'll see if we've missed anything. I feel like we have.
I think we have.
So let's see. I'm going to load word, restore the stack pointer. T0 for SP, RA, 0 SP, this is going to be SP. Okay, so let's go and trace through it really quickly with the function call, just to test our code. And I recommend you do this, even if it's quick, on your test, just to make sure that what you wrote down makes sense. So give your function that you write a test run. So I'll do 3, or I'll do 3 to the point now. And we expect this to return 81. That's what we hope to get. Oh boy. So, let's go and run through it quickly. Initially, A0 is going to be the value 3, and A1 is going to be the value 4. So we enter. It's not 0. So because it's not equal to 0, we branch. So we branch over here to the recurse label. And so we make room on the stack to store RA and T0 on the stack. And then after this, T0 is going to hold the value of 3. That's our base. We're going to decrement A1. And let's do that. A1 is now being decremented. And it holds the value 3. And then we're going to call the power function. So now we return back to the top. Same deal. We check if A1 is if it's non-zero. It is non-zero, so I branch, make room on the stack. I reassign this the value of A0. Well, that doesn't change it. And then I decrement A1, so now that's at 2. And then I call my function again. And so I keep doing this. Exact same thing's going to happen, and it's going to be a 1. And then the exact same thing's going to happen, and it's going to go down to a 0. So we went through it a total of 4 times. And so this is the 5th time through it. So on that 5th time through it, we enter. We check is A1 non-zero. Oh wait, it is 0. So we can't branch. and we instead do this. So on this line, we're changing A0. And when we change A0, we're going to set it to 1. That's the return. And then we go ahead and return to our caller. This JRA is going to bring us all the way down after this jump and link, where we're back now in the 4th iteration. We just finished the 5th. That was the base case, where the power was equal to 0. Now here, in this case, the power was equal to 1. And so we get, okay, we're going to take our return value, which is 1, multiply it by t0, or sorry, we're going to take t0, multiply it by our return value. T0 holds 3, times that by 1, and you get an output of 3. So A0 is going to be 3 after this. And then I load T0 from the stack, I load my return address from the stack, and I restore my stack pointer. When I load T0 from the stack, it's still 3. That's fine. Like I said, we don't need to do this step, but I'm doing it anyways. We figure out where we're supposed to be returning to, we restore the stack pointer, and then we return. So now we're done. This was the case where power was equal to 1. Now we're back in the 3rd call, where power was equal to 2. So in here, we'd say, okay, we just ended up here. A0 from the previous one, we returned to 3. At this step, we're going to do T0, which is 3, times A0, which is 3, to get 9. And that's going to be stored in A0. We're going to restore T0. It's going to be 3 again. We're going to restore our A. That's our new return value. And we're going to restore our stack pointer. So now we're done with this one. And we've returned 9. And at each stage, this has made sense, because in the 5th stage, our return value was 1, which is what you expect for the base case of 0. In the 2nd case, our return value was 3, which is what you expect for p equals 3, and our return value was 9 for the last. So this seems to be like it's working. If we move on to the 2nd one, that's where p was equal to 3. We return here. Our previous return value was 9. 9 times 3 is 27, so A0 is going to be 27. We restore T0, we restore the return value, restore our stack pointer, and we go back again to the very first function call, where p was equal to 4. Is equal to 27. And so on this last one, we read back in T0, 3, which is multiplied now by A0, which is 27. So we have 3 by 27, that's going to be 81 bricks. Store that in A0. Restore T0, restore our A, restore the stack pointer, and jump back to our original caller. So it works. Now the reason why it works, and I did this incorrectly if T0 had changed every time, is I should have, if T0 changed every time, loaded here
There.
before
Yeah.
the multiplication instruction. And it's very easy to miss that that's the case because T0 actually stays the same the whole time in this example. If you're doing it with a different example, you'd see that you only restore it after you actually needed it. So you were too late. So this should actually go up above. Again, however, for this particular case, you could omit that line and omit the storing of it and have just one stack space allocated, and it would still work.
Cool.
Okay, any questions?
Wow, that was perfect.
All right, I'll go ahead and stop the recording.